In this video, we try to see what is the correlation and autocorrelation of a continuous time signal. The correlation function is used to indicate the degree of similarity between two different signals. So, higher the value of correlation function is more the degree of similarity between the two signals. Whereas autocorrelation function is provides the measure of similarity between the signal x of t and its time delayed version x of t minus tau. So dear students, here the correlation is used to measure the similarity between the two different signals, whereas autocorrelation function is used to measure the similarity between the signal with itself delayed signal. So first of all, we'll try to see what do you mean by autocorrelation. Here in this formula, the autocorrelation is indicated by r of tau is equal to integral minus infinity to infinity. X of t is the signal, which is the energy signal, and x of t minus tau is the delayed signal of x of t. Tau is the delay. The integral is with respect to dt. Otherwise, we can say here t plus tau. Okay, this is the advanced delay and this is the advanced and this is the delayed signal and this is the advanced signal. So if signal x of t is the complex value signal, then the formula becomes this. Where in the block diagram it is shown same. So x of t is the original signal, okay, and we provided it's a delayed signal. Integral gives us the autocorrelation of the signal. So when we'll get the autocorrelation maximum, when there is a delay is equal to tau is equal to 0. At that time we will get the maximum autocorrelation, that is the signal itself is the similar and autocorrelation function is the maximum. As in the previous video we seen what do you mean by ESD. Okay, so ESD is indicated by the symbol psi of f. Okay, so here in the ESD topic we seen the properties of the ESD. In that property we seen already that autocorrelation function is the and the ESD is the Fourier transform pair. So autocorrelation function and energy spectral density forms a Fourier transform pair. This property we try to prove here. As already we seen what is the autocorrelation. Autocorrelation is x of t into x of complex conjugate t minus tau dt. Okay, so now here we are using the inverse Fourier transform formula in place of x of t minus tau. We are saying in terms of inverse transform. So x of f into e raised to minus j 2 pi f. In place of t we are substituting here t minus tau integral with respect to df, because it's a inverse Fourier transform formula. Take the conjugate on both sides. So because of that, x of t minus tau conjugate becomes e raised x of f e raised to, so entire conjugate means x of f conjugate. Because of conjugate, plus sign of e raised to j 2 pi f t minus tau becomes minus j 2 pi f t minus tau. Substitute this equation in the equation number 1. So we replace x of t minus tau conjugate with this entire expression. So rearrange this two integral term. So we taken outside this x of f conjugate into e raised to j 2 pi f dt, and here we are getting indirectly the Fourier transform formula. So x of t into e raised to minus j 2 pi f t becomes x of f. So what we are getting inside the integral, x of f multiplied by x of conjugate of f into e raised to j 2 pi f tau. So this is indirectly x of f square e raised to j 2 pi f tau. And already we seen what is the x of f square, which is nothing but the psi of f, that is the ESD. So we substituted in place of x of f square psi of f into e raised to j 2 pi f into df. So that is nothing but the inverse Fourier transform. So hence we proved, if you try to take inverse Fourier transform of ESD, which is in frequency domain, we will get the autocorrelation function in time domain. So hence we proved that these two, autocorrelation function and ESD, are the form inverse Fourier transform pairs of the each other. In the similar way, autocorrelation function of a continuous time power signal. So the autocorrelation function of a power signal is a measure the similarity between a periodic signal x of t and its delayed version x of t minus tau. The autocorrelation function over one complete period t0. So now here we are considering the given x of t is the power signal. So hence the formula is slight change here, as we have to consider it's a period. So integration becomes minus t by 0 to 2 plus t by 0 to the x of t into x of t minus tau dt. So this is the autocorrelation function of the power signal. So the interrelation between the autocorrelation and PSD is the similar. This property also we seen previously, that autocorrelation function of the power signal forms the Fourier transform pair with the PSD, that is power spectral density. So if you try to find out autocorrelation function which is in time domain, take the Fourier transform, we will get S of f, and S of f inverse Fourier transform is nothing but the autocorrelation. Okay, now we will see some numerics. So numeric number 1 is determine the autocorrelation of the following signal. See here, students, we have to find out the autocorrelation, means the signal with we try to find out the similarity between the signal with itself with the delayed signal. So original signal is x of t sine omega 0 t. Already we know it's a sine omega 0 t is the periodic signal. So normally periodic signals are the power signal. So here we are referring the formula of autocorrelation of the power signal. So r of tau into is equal to 1 upon t0 integral minus t0 by 2 to plus t0 by 2 x of t into x of t minus tau into dt. So what is x of t here? Sine of omega 0 t. So substitute x of t with the sine omega 0 t. Substitute in place of x of t minus tau sine omega 0, replace t with the t minus tau dt. Here we are using the trigonometric formula sine A sine B is equal to 1 upon 2 cos A minus B minus cos A plus B. Okay. So after substituting this trigonometry equation and after simplifying this, we are getting r of tau with the integral 1 and integral 2. So in the term 2, in this term 2 is a cosine wave of a frequency f0 and phase shift of omega 0 tau. If integrate sine and cosine wave over its one cycle, then the result of the integration is 0. So hence what we remain here, so indirectly this cos integration becomes 0, as this cos of omega 0 tau with respect to integration is dt. So this is the constant term. So what is the integration here? See, I'll repeat again. R of tau is equal to 1 upon 2 0 integral minus t0 by 2 to t0 by 2 cos o minus omega 0 tau dt, as this integration is with respect to dt. So and this cos term is with respect to tau, so this treated as a constant, correct? So what remains? 1 into dt. So one integration is t, substitute this limit, what is the output? 1 upon 2 cos omega 0 t. So here because of entire cos, now here omega 0 t, so that's why this integral answer becomes 0, correct? So now here what we are getting, r of tau, that is the autocorrelation function. Okay, now what we have to find out? We have to find out the power. So the another way to find out the power is what? Simply substitute tau is equal to 0. Okay, so when tau is equal to 0, so tau cos of 0 becomes 1. So what is the power here? Half. Okay, so this is the another way to find out the power. Either use our normal formula P is equal to 1 upon T integral minus T by 2 to plus T by 2 x square of T into dt, or find out the autocorrelation. After solving the autocorrelation with respect to tau, substitute tau value is equal to 0, means indirectly delay is equal to 0, we will get the maximum value of the signal, which is nothing but the power of the signal, that is 1 upon 2. Next numeric is same. Okay, now in place here the question is sine 6 sine 2t. Okay, the entire process to solve this numeric is similar to the previous numeric. Okay, I solved here the each and every step in detail. Okay, so go through it. Okay, again we'll find out here the autocorrelation function. Substitute tau is equal to 0, we find out here the total power. Okay, now in the same numeric we try to calculate the power spectral density also. So what is the power spectral density? S of f. And here we are using the autocorrelation property, that if we try to take the Fourier transform of autocorrelation, which is here autocorrelation r of tau is equal to 18 cos 2 tau, If we try to take the Fourier transform of autocorrelation, means we are getting power spectral density PSD, and cos Fourier transform is 1 upon 2 delta f minus f0 delta f plus f0. Okay, in from this equation, given equation, the omega is equal to 2. By that we will in the position to find out the f, substitute here the f. So this is the power spectral density of the given signal. Okay, so in the, here now next topic is the cross correlation function, which we will continue in the next video. Thank you.